Alright guys, welcome to chapter 5. Thank you for watching our video. On this section we are going to cover two topics, area and something called Riemann sums. So we're going to talk about area and Riemann sums. Alright. First thing I want to do is, in order for you to understand how we're going to find area and what Riemann sums are, is I need to introduce you to the concept of sigma. You've already encountered this on pre-cal, so it's just a refresher. Sigma notation. You know from pre-cal, that's the Greek letter sigma. Agreed? And the Greek letter sigma in math means the summation, right? So I'm going to write this and break it down for you. So right now I have a summation, right? This right here is known as the index of summation. It tells you that you start at 1 and that you finish at the nth term. Well, how does that help you? What that tells you is that everywhere you see I, you're going to plug in 1, and then 2, and then 3, all the way till you get to n. So if you do that, you get a sub 1 for the first term. Plus, you plug in 2, a sub 2. Plus, a sub 3. Plus, so on, all the way until you get to a sub n, which would be the last one. Agreed? And you add them all together, because that's what sigma tells you to do. Yes. Okay. This right here are known as the elements of summation. We're okay? And technically this right here helps you find the ith term. So the first, the second, the third, the fourth, the fifth, etc., right? All the way to the nth term. We good? Move closer. I don't smell. Come on, move closer. I take a shower every morning. Alright. So we got this helps you find the elements, and once you find the elements, you can add them together, right? The reason why I'm showing you this is because we are going to use rectangles and trapezoids today to find area under a curve. So we're going to have to find the sum of the areas of each one of these rectangles and each one of these trapezoids and add them together. We're good? Now, before we get there, I want to show you some properties of summation, and we're going to practice just something very simple so that you understand how this works. Okay? So let's say that you have the summation from 1 to 5 of I plus 1. How would that look like if you expand it out?
2 plus 3.
So 1 plus 1, which is 2, plus 3 if you plug in 2, right? So on until you get to, right? There's 5 terms. You went from 1 to 5, the first, the second, the third, the fourth, the fifth term. Yes? Once you find your elements, you're going to add them. So that's 5, that's 10, that's 20. We okay? Now we're only going to do one example because we're in calculus. This is just a refresher. We're okay with that?
Yeah.
Now, this is what is new. So even if you took notes last class, I do need you to take notes over this. I'm going to share with you some properties of summation.
Wait, is summation going to be used in equation?
Summation is going to be used throughout the entire chapter 5, chapter 6,
Great.
okay, and beyond. Okay? Yes, sir.
So like, let's say you wanted to do like, if you wanted to increment it by half, would you like double the top one and then just like divide by 2? Wow.
Alright, here's some properties. Let's say that I have the summation from 1 to n, right, of k times a sub I. Cool? K is just a constant. And this property is the same property that we use for limits. Do you remember that if you have a constant with a limit, what can you do with the constant?
Take it out.
Take it outside of the limit. So we can do the same thing with summation. We can take it out of the summation, and this would become k times the summation from 1 to n of a sub I. Cool? Are you okay with that? It makes the summations easier, right? Imagine multiplying every time by k, rather than, hey, finding the sum and then at the end multiplying by k, right? The other one, and I think, again, it makes a lot of sense, is something like this. Let's say you have the summation from 1 to n of a sub 1 plus or minus b sub I.
Is that complex?
What do you mean? No, these are not complex numbers. We're not talking about imaginary numbers here, okay? That's just the ith term, okay? So something plus something else, right? So some...
Does I stand for iterator?
I don't know, actually.
Yeah.
Hmm.
Because in computer science, we have like
Iteration? Is that what you said? I'll look it up. I don't know, honestly. Okay. I thought it standard, like, I thought he meant for index. That's what I thought.
Gotta get in there.
Anyways, so what you can do here is the same thing you did with limits. Remember that with limits, when you had a plus or minus, you can break it up into two limits? Well, here you can break it up into two summations. The summation from 1 to n of the first one, plus or minus the summation of 1 to n of the second one. Okay?
Like about previous problem, you could have done,
Yes, so the problem above, I could have done the summation from 1 to 5 of I plus the summation from 1 to 5 of I. I'm sorry, 1. Okay? Yes, sir. Why is that easier? Because what if you have a summation from 1 to 1,000? And you have to add 1,000 terms. Right? And we have more to help you. Because what if, like, I have 2,000, 5,000, 1 million? Because eventually, remember last class we talked about, we want to increase the number of rectangles and take them to infinity so that we can find the area under the curve. Well, sometimes you're going to have very large numbers, and there's no way that you're going to sit there and find the area of 1,000 rectangles and add it together. Okay? I mean, yes, do it if you want to. Just spend all your time doing that. So I'm going to give you some properties that will help you out. Okay? Are we okay with this too? Then that takes us to 4 more. Now the next 4 are very helpful, especially for what I just mentioned. What if you have to add up like 1,000 terms? Okay? So let's say that you have the following. The summation from 1 to n of just a constant. This is an easy one. Just a constant. It's just itself times the number of terms. Right? Think about it. That makes sense, right? Like if it was 2 plus 2 plus 2 plus 2 plus 2 a bunch of times, like 1,000 times, it's a lot easier to just do 2 times 1,000, right? Okay, so that one is a given, and you already know that one. The next 3 you do not know. We will not do the proofs. I'm sorry, guys. We do not have time to do the proof, so you're just going to have to accept them as for what they are and apply them, okay? So the summation of 1 to n of I. What that means is if you plug in 1, it will be like 1 plus 2 plus 3 plus 4 plus 5 all the way to n. Okay? What do you think it is?
n plus 1 times n plus 1 times n divided by 2.
Good. It's n times n plus 1 over 2. Can you guys tell Brian his time is up? Thank you. So, rather than, let me just kind of show you this. Let's say that the top number was 1,000. Rather than finding 1,000 numbers and adding them all together, you will literally just plug in 1,000 times 1,000 plus 1 divided by 2, and that will give you the sum of all of them, rather than finding each one of them individually. Okay? Alright. What if you have something like from 1 to n of I squared? So this time is 1 squared plus 2 squared plus 3 squared all the way to n squared. Yes, ma'am?
Now, is I just a variable, or does I...
I is the numbers that we're plugging in from our index. So like the 1, yeah, it is a variable. Treat it as a variable. So
It's not a function. So would it be...
we will use it as a function eventually.
So if that's like 2x plus 5 for the second time that you wrote, and times n plus 1, would that be 2x plus
Okay? Now, the formula for this one, I'll explain what she meant here in just a second because we're going to try it. Okay? The formula for this one is a little bit larger. It's n times n plus 1 times 2n plus 1 divided by 6.
Wow, good for you, Brian.
Okay? Now, we're going to cover one last one in this class because technically there's one for I to the third power, to the fourth, to the fifth, like to any power. We're just going to go up to the third power. Okay? So to the third power, this one looks a little different. N squared times n plus 1 squared divided by 4. Okay? Ready?
Yeah.
We're going to apply them. You got them down?
Could you prove the second one?
We don't have time for proofs right now.
60 seconds.
Dude, we have a lot to cover. I'm sorry. Okay? You already know the proof. Why do you even want to prove it?
Because I want to spread knowledge.
Stay after class and you can spread knowledge to whoever stays.
I will.
Okay? Alright. Example.
Now they don't really know what's happening.
Evaluate the following. Let's say that you have a summation from 1 to 1,000. From 1 to 1,000 of I plus 1. Oh, I'm sorry, I wrote it down. I plus 1 over n squared. I wrote it down wrong. I'm sorry. There it is. I plus 1 over n squared.
Oh, is n squared always thousand?
Okay, stay with me. Hold on. If you were to find every single term, you would plug in 1, and then 2, and then 3. But we have a problem. What are you going to plug in for n, right? Like, it's two totally different things, right? You have I and you have n. Agreed? You would need a function, which you do not have right now. No. So there's no way to solve this other than by using the formulas up there. Okay? N is just going to be a constant. It's just going to be a number, because you're going to plug in something in there. Agreed? You with me? So I can rewrite this as, yes sir,
1 over n squared.
1 over n squared times I plus 1. Are you okay with that? Yes? That's the same thing as that. This is just a constant, right? What can you do according to the properties with a constant? Take it out of the summation. Yes? So I'm going to rewrite this 1 over n squared. And do you notice that I can also split this up into two summations? According to the properties? So times the summation from 1 to, and here's where I'm going to change things up for you. Okay? I'm going to put this as an n. Okay? And I'll explain to you here why in just a second. Of I plus the summation from 1 to n of 1. Okay? Now, the reason why I changed the 1,000 to n is because we're not going to use the 1,000 until the end. Oh, thank you, sir. So I'm just going to go to the side and remind myself that I need that at the end. Okay? Yes, sir.
Can you take the 1 out of the summation?
Yes, we can, but technically we'll still be left with a 1 in there, right?
Yeah.
Well, it just
It just cleans
n,
it.
right?
Now, stay with me. Yes, sir.
But then, how do you know that's a constant, like 1 over n squared?
How do I know what? I'm sorry?
Like, you see where it says 1 over n squared?
Uh-huh.
Then, how do you know that that's, like, it was like 1 over x?
Because it was from the beginning. It was. Remember how it's always to the n? You're saying?
Then, yeah, no, it's not just some random variable.
It's not just some random variable. Okay? Alright. You guys okay so far? Well, this looks very familiar to me. Both of this. What is this equal to according to the properties I just gave you?
1,000 times 1,001.
Wait. Don't use numbers. What is this equal to? The I.
Times n plus 1 over 2.
So instead of having a summation, I'm going to replace it with n times n plus 1 over 2. Are you guys okay with that? Yes? You with me? The whole purpose of doing this, guys, is that we want to get rid of the summation symbol. It's no longer there. Now this one is just a constant. What does the constant rule tells you to do? N times 1, right? So it's just going to be... Are we okay? Now we just got to simplify this out, and we will be ready to answer a question. Okay, if I multiply this in, do you see how the n's would cancel out?
Yeah.
So you would be left with n plus 1 over 2n. Yes? And if I multiply this by that, I will be left with plus 1 over n. Yes? One last step, just put it together as one fraction, and that's going to be over 2n, right? And that will become a 2, right? So then n plus 1 plus 2 is n plus 3. Do you see the summation symbol anywhere? No. What was n? 1,000 plus 3 over 2,000 equals to 1,003 over 2,000, and that would be your answer. And now here's the cool thing about this process, because let's say that now I ask you, hey, can you find this for 2,000? Now you're just going to plug it into there. Can you do it for 5,000? Now you just plug in there, and so on and so on. So if I wanted you to get a better and better estimate of an area, you will continue to increase the number, and you will start to see a pattern to be like, oh, this is getting very close to a certain number, so I'm going to predict that the total area is maybe this much.
Would you just do a limit?
Eventually we're going to get there. Okay?
As n.
Do you guys see the value of this? Yes? Can we move on, or do we need another example? Move on? All right. Then let's talk about area under a curve. The area of a plane region. First of all, let's say that you have f of x, and I'm just going to keep this problem easy for notes purposes, equals to x squared. F of x equals to x squared. Okay? And I only care about f of x equals to x squared on the interval from 0 to 2. Okay? I want to use 4 rectangles of equal width to find an approximation of the area under the curve between the x-axis and that curve. So the first thing we're going to do is we're going to give ourselves a sketch of what this looks like. So I'm going to say that every 2 spaces is 1. Okay. So at 2, 2 square is 4, so I'm all the way up here. 1 square is 1. So this thing looks something like that. Okay? Now, I only care about from 0 to 2, so I'm not going to grab anything else. What I'm going to now do is I am going to take that region, and I need to find the area that's underneath that region that is enclosed with the x-axis. And I need to divide it by using 4 rectangles. Now, last class, you found out that there's 2 ways of using rectangles here. Okay? First of all, you want them to be all equal width. So to find the width of a rectangle, you're going to use the following formula. Delta x equals to b minus a divided by n. This is a, this is b, and n would be your number of rectangles. So for this problem, delta x would be equal to 2 over 4, which is 1/2. We are going to use rectangles of width 1/2. From 0 to 2, that will create 4 rectangles. Agreed? Now that means that I'm going to have a rectangle here, 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 and here. Yes? The question last class was, well, do I start on the left or do I start on the right? It will matter. So ready? Let's say that I use the left endpoint. I'm going to use blue for left. Okay? So left and then I'm going to use red for the right. Okay? So if I go to the left, starting at 0 and I go to the left will be here, right? If I go up, well, I'm not going anywhere, right? That's it. With me? Then I move on to the next one. Here's my first rectangle, not triangle. Then I go up on the next one, and I go up. Then I come over. That's my second rectangle, right? Then I go up. That's my third rectangle. Yes? And last but not least, I go up, and that's my fourth rectangle. Based on this problem that I'm doing, do you see how using the left endpoints are going to give me an underestimation of the area? Because I'm missing all this space in between. Now I could do that, or I could use the right. If I use the right, when I overestimate, right? So if I use the right, I'm going to start here. Go up, goes this way. Yes? Go up, goes this way. Go up, goes this way. Go up, and goes this way. So it's definitely an overestimation. But what we can do for sure is we know that the actual area is less than the right endpoints, but it's greater than the left endpoints. Okay. There's a third method, but I feel like if I put it in here, it's going to get just really messy on the diagram. Okay? Alright. We're going to do all this with this problem. Okay? Now, I'm not going to use those formulas of summation that I just showed you for a reason. There's only 4 rectangles. That's not bad. Could you use the formulas of summation that I showed you? Yes. I'm going to start the problem to show you how you could, but I'm not going to actually do it because it takes forever to just answer the question for 4 rectangles. Okay? Let's say that I want to do the left endpoints. Okay? I have the 4 rectangles. Agreed? So the left endpoints, the area, would be equal to, well, we know that the area of a rectangle is, in this case, the width times the height, right? So we basically have these rectangles where you have delta x being your width, and then you have some height. Well, you know delta x for the first rectangle. What's the 1/2? And if I'm using the left endpoint, the height would be determined by finding the value of the function of the left point, which in this case is f of 0. Yes? That will give us our first rectangle. Plus the width times the height of the second one, which would be f of 1/2. Yes? Plus 1/2 times f of 1 plus 1/2 times f of 3/2. And that would be the underestimation. Well, do you remember for pre-cal how we can come up with an expression to represent this? The summation from 1 to 4. Notice how 1/2 is repeated here. What does the 1/2 represent? It's a constant width, right? And aren't you figuring this out by, isn't it width times height? So isn't it technically f of something times the width? Yes? Well, we need to come up with a rule that's going to work here. So if I put, let's say, f of I, will that work? Because then I would start at f of 1, and I'm not starting there. I minus 1. 1 minus 1 is 0. 2 minus 1 is, but is it like that, or is it going to be over 2? Or over 2. Yes? Agreed? So check. Will it work? The 1/2 is there, right? If I plug in 1, 1 minus 1 is 0, 0 over 2 is 0, right? 2 minus 1 is 1 over 2, 1/2. 3 minus 1 is 2 over 2, 1. 4 minus 1 is 3. Agreed? Now, how can this be used with what we just came up with earlier? Let me clean it up because it's a little blurry.
We didn't derive any.
Okay, that's where we're at right now. Yes? Yes, ma'am. Oh, you're just stretching?
Oh, yeah.
Okay, guys, you ready? Stay with me. Notice that this says evaluate the function here. Yes? Do you have a function? Yes? So doesn't this technically become the summation from 1 to 4? What's the function? All the way up top it was x squared. So that means that this is I minus 1 squared times delta x. Yes? Well, delta x is equal to 2 minus 0 over n, which is 2 over n. I'm not going to use the number of partitions, because remember, all those properties is so that you can find as many partitions as possible, not just for 4. Like, what if I want to do 1,000 rectangles? So I want to keep it in terms of n. Okay? So that means I'm going to replace that with 2 over n. Yes, sir. F, this is the function. This is the function, right? Okay, stay with me. We're good so far. Well, you know how to do this algebraically. Oop. I minus 1 squared is going to be I squared minus 2i plus 1 over 4 times 2n. Yes? Yes, ma'am. What's that? We were using the 4 rectangles. I'm not going to do that until the end. But I agree. I think I know where you're going with this. So that I can replace it, you want to keep an n. Right? Is that where you're going with this? Yes, we're going to come up with one basic expression that would work for 4 rectangles, 100 rectangles, 1,000 rectangles, and so on. Okay? So technically you are correct. I should not be putting the 4 there. I should be putting an n. Okay? Alright. Now, if you look at this closely, I can multiply the 2 in and I can multiply the... Well, actually there's no need to do that because isn't this just a constant?
Yeah.
Good. I'm going to pull it out of the summation. Yes? But even further, I'm going to take out the 4 as well. So 2 over 4 is half. So 1 over n? 1 over 2n, I'm sorry? Yes? 1 over 2n to the outside. And what would you be left with? I squared minus 2i plus 1. Yes? Do you guys see where I'm going with this after this? You know I square, right? You can replace it. Agreed? You know I. I is n times 2, n times n plus 1 over 2, right? And you know that the summation for a constant. 1 over 2n times the summation from 1 to n of I squared minus 2 times the summation from 1 to n of I plus the summation from 1 to n of 1. Agreed? According to the properties? Now, I'm going to flip the page. No? Let's go here then. 1 over n. You know what this is right here. What is I squared? What does this become? N times n plus 1 times 2n plus 1 over 6 minus 2 times what's I? N times n plus 1 over 2. And lastly, plus 1 is just going to be n, right? Okay. I don't want to finish this problem because, again, it's pointless for the amount of rectangles we have. Look at all the work we're doing. But what if I ask you for 1,000 rectangles? Do you see how this would be the way to go? From here you can start simplifying out, and once you get done, I could ask you, hey, what would the area be if we have 1,000 rectangles? What are you going to have to do? Plug in 1,000 and you get the area. Okay? Are we okay with that? Like, can I stop right here and you will be okay? Yes, sir.
Is that the area under the curve, or is that just the area
Of the rectangles. The rectangles.
the actual area?
No, it's still be an approximation. Okay, it's still be an approximation. Okay?
Are there integral rules?
Yes.
Are there integral rules?
Yes. We are going to do that. Okay, pause, guys, because this video is just so that you can see how this is done. I don't want to repeat all this, because I can do the same thing for the red. Agreed? You guys with me? But instead of being I minus 1, it's going to be just I over 2, and then the entire process repeats. It's not going to be exactly the same, but it's going to be very similar. Do you understand? Here's what I need you to understand. That the red, in our case right now, will give you an overestimate. The blue will give you an underestimate, and the area is actually in between. And to improve that approximation, we can increase the number of rectangles to get a better and better and better approximation of what the actual area is. Are we okay with that? Yes? If you don't have that many rectangles on the AP exam, do not waste your time doing this. It's too much. Too much work, and you don't have that time to do it. The AP exam is not to prove that you can do it. Like, that you can do this.
Will they give you the number of rectangles?
Okay? Yes. Okay? Are we okay with that? Alright. So, can I move on from this problem and... Yes? Alright. The last thing I want to show you with this one is how to use a trapezoid. Same problem. From 0 to 2. But instead of using rectangles, we can use a trapezoid.
Oh, what?
Are you not using the midpoint?
Just a second. Okay. This thing still looks like... I'm just going to make it up. I'm not going to draw the scale. There you go. Okay? Yes? This is 2. This is 1. Cool. If I want to use 4 trapezoids of equal height, the reason why I use the word height, I'm going to pause the video for just a second. The reason why I said equal height is because you got to remember that a trapezoid looks something like this, where this is a base, this is another base, and this would be considered your height. And what we're going to do...
Wait, I thought...
It's plain. What we're going to do is we're going to use this trapezoids like this. So we want this to be the same throughout. Okay? So we want 4 trapezoids of equal height, so that would be 2 minus 0 is 2 divided by 4, that would be 1/2 once again. So that would be right here, right here, right here, and there. Agreed? Here's the easy thing about trapezoids. Once you determine where you're at, you don't have to worry about left or right. Literally, just draw a line going up to the curve.
Wait, equal height? Wouldn't it be equal width? No.
Again.
Oh,
Okay? Alright. Now, all you gotta do is make it look like trapezoids by connecting the bases. From here to here, from here to there, from here to there, and from here to there. Do you see how this would be the best approximation we've done compared to the left and right endpoints? Now, unfortunately, there's not a way that we can do all that hard work that we did for the previous one with a trapezoid. So you're literally just going to have to add each trapezoid. You know that the area of a trapezoid is equal to base 1 plus base 2 divided by 2 times the height. Yes? Well, if you look at the very first trapezoid, the area is going to be, the base 1 is the left endpoint. Agreed? Which is f of 0 plus f of 1/2 would be the second base, divided by 2 times the height. The height in our case is delta, which is 1/2. Plus, the next one would be f of 1/2 plus f of 1 divided by 2 times 1/2. Yes? Plus f of 1 plus f of 3/2 divided by 2 times 1/2. That will be 3, and our last one would be f of 3/2 plus f of 2 divided by 2 times 1/2. It's a lot of work to be doing this. Luckily for you, we can simplify this out for every single time you try this. Yes, sir.
Did you do the sum of, like, couldn't you figure out the sum because it's always going to be 2 on the bottom?
Mm-hmm.
Take out 1 over n.
So we can take out the 2 right here, and we can take out this 1/2 as well.
Yeah.
I'll get back to what you're saying here. So that would be a 1/4, right? If you take that out, you're literally going to be left with f of 0 plus f of 1/2 plus another f of 1/2, making it 2 of them, plus 2f of 1s plus 2f of 3/2 plus f of 2. Notice there's a pattern for this, and this pattern will always happen when you're using trapezoidal rule. Technically, here's what the rule says. You ready? Area is going to be equal to delta x over 2. If you think about it, that's what happened, right? The 1/2 was multiplied by our delta x. Our delta x was 1/2, right? That's how we got the 1/4. And you're going to have then this pattern starting with the left end point. Okay? And then you have all this in between where there's 2 of them, right? F of something. Let's see. Hold on. And then this would be I minus n. Okay? You with me? Just trying to come up with something. And so on. There's always 2 of everything in between, but just 1 at the endpoints. And that works every single time. So if we try it for this one, going back to that problem, 1/4. F of 0, 0 square is 0, plus 2. F of 1/2, 1/4, plus f of 1, plus f of 3/2, 9/4, plus f of 2. Yes? Okay, so I have 1/4 times 2 times 1/4 is 1/2 plus 2 plus 9/2 plus 4. Agreed? So I got 6 plus 5, 11 over 4. Cool? And that's just the area of the trapezoid. Still not the area under the curve exactly. Yes, sir.
Is this where they got, like, negative 1/12 for the sum of all the natural numbers? Like, using this?
Are you talking about that number problem?
Yeah,
video?
like, what?
I'm not sure.
Stop.
Why?
I watch a lot of number file too, but I don't want to watch a proof of that right now.
Okay.
I was just
Stay with me. I'm not sure, man, honestly. Okay? Alright. What you've been doing here, this is called a Riemann sum. Some guy named Riemann started playing with, hey, let's figure out what the area is of these things, right? So he started using rectangles. Now, here's the thing. And I want to make this very clear, so if you're watching this video and you're not even on my class, like you're just watching this video because you run into it on YouTube,
Okay.
we do not cover on my class rectangles that are not the same width. Because technically we can do rectangles of different widths. Nowhere does it say that we have to use rectangles of equal widths. So Riemann actually thought of that, and he was like, well, what if we start using rectangles of different widths? And he started playing with it, where he started with a thicker rectangle and then a smaller and smaller and smaller and smaller and smaller and smaller and smaller as he moved to the right. Okay? It eventually led him to what we're going to go, which is called integration. Okay? We don't cover that in this class. It's not on the spec of this class, so we're only going to be using equal with rectangles and equal with trapezoids. Okay?
So what's the difference between integrals and integration?
It's the same thing.
Okay.
Integral and integration is just different words for the main same thing.
We're
Okay?
not
Not yet. Okay?
Not yet.
Stay with me. Which then takes us to the following. The definition, and this is brand new. So now this is brand new. Definition of a definite integral. Definition of a definite integral. The limit as delta approaches 0 of the summation from 1 to n of f of c's of I times delta x is equal to the integral from a to b of f of x dx. Yes. The limit as delta x approaches 0 of the summation from 1 to n of f of c's of I times delta x is equal to the definite integral from a to b f of x dx. I'll explain all this in just a second, okay? The fact that we're not using rectangles of different widths makes it a little bit more difficult to explain this, so stay with me. Riemann decided to use rectangles that were decreasing in width as he moved to the right, therefore explaining that the delta x is approaching 0. In other words, the width is approaching 0. Do you see with me? This just represents what we've been doing, just rectangles, width times height. The reason why this says c's of I is because this is going to change every time if you think about it, right? It changed for us every time as well. The height kept changing. Agreed? So what this is saying, if you were to add all of these rectangles of different widths and you were to take the limit of that, it gives you this. This is called an integral. I will continue to explain. You're not going to be very clear what this means today, next class, and what it does. What I tell you it does is that this is how you undo a derivative. That's as much as I can tell you for right now. Okay? It leads up to this. And this is called a definite integral because you have boundaries. This right here is known as a lower limit. And this right here would be your upper limit. I think you know what f of x is. And d of x literally just refers to the variable of, in this case, what are this called? Integration? Yes? Variable of integration.
And what is that?
Stay with me, dude. Okay? I promise you. I have to really just show you all this before I can jump into integration. Okay? Yes?
What does the C mean and the F is C?
These are the values. Remember how we were plugging in values to find out the heights? So it's going to be different every time. Okay? We're good so far? Yes? Okay. Here's where eventually this Riemann basically got to the definition of this. He discovered, and it's not going to make sense today, and it will in a future, that the area under a curve is actually all this that he was doing. So that means I'm just putting this up for you finally. The area is equal to the integral from a to b of f of x dx. That's it. This, he discovered that this method gets you the exact area without having to use rectangles and adding them up individually. Okay? I am not going to show you how to integrate today. I'm just introducing you to the notation. Okay? Since you still don't know how to integrate, we are going to use your knowledge of geometry to help us out. I want to
So we have no help at all?
integrate the following. Do you notice how this basically says, hey, find the area between 1 and 3 of this function, right? Well, we don't know how to integrate yet, so we're going to have to grab this. What does the function of 4 look like? A horizontal line at 1, 2, 3, 4. So here's f of 4. I mean f of x equals 4, right? So here's, yes? Do you notice how this tells you between 1 and 3? Well, here's 1, 2, here's 3. I want that area. You don't need calculus to answer this. What is that? Okay? Next one. The integral from 0 to 3 of x plus 2 dx.
Wait, why would it be? Oh, never mind.
Yep.
I thought that said 0. I thought it'd be 4.
Alright, isn't this just a line with a slope of 1 starting at 2? Going from 0 to 3? So I'm looking for that area. And you know how to find the area of a trapezoid? Base 1 is how much? Plus 5? Times 3, right?
Wait, so, for integrals, the constant matters, but for derivatives, it doesn't matter.
Say that one more time.
For integrals, like, the constant, like x plus 2, it matters, because, and then for derivatives, it doesn't matter.
Correct. Yes. So 21 over 2?
Oh, is that why there's something like mu equals to, like, plus p? That's integration.
Yes.
I understand the mu now.
Okay, are we good so far?
Yeah.
So in other words, you don't know how to integrate, but you know geometry? If you know your basic geometry, you should be able to integrate this types of problems so far. Alright? Last one. From negative 2 to 2, square root of 4 minus x squared dx. Okay, that's a little tougher to graph, but you can do it. Alright, so it's from, it's negative 2, so I went. Alright, if I plug in negative 2, negative 2 square is 4, 4 minus 4 is 0, square root of 0. So I have negative 2, I'm at 0. If I plug in 2, I'll be at 0. If I plug in 0, I get 2. It's a circle. Yep, semicircle. Very good. Do you know how to find the area of a semicircle? Area equals 1/2 pi. Well, the radius in this case is going to be... Yes? Do you understand why I put the 1/2? So I have just a half circle. So what is this? 2 pi? And we're down to our last page of notes. This has been a long video. Long class. Sorry. How we doing? We're good? How's the climate compared to first period?
Learning.
More what? I don't know what you just said.
It means
Okay. Alright. Now I'm going to share with you properties of integrals, just like we had properties for limits, just like we have properties for summation. I'm just going to show you some properties for integrals. Okay? So first of all, we have two very special ones. The very first one is, let's say you have an integral of f of x dx that goes from A to A. What do you think that's equal to? 0. That's like no area whatsoever. You didn't even move. Yeah, properties of integrals. Okay? The next one would be from B to A, where B is greater than A. We can't do that. The lower limit has to always be smaller than the upper limit. And right now, I'm saying that B is bigger than A, so we can't make that happen. So for us to accomplish that, I want you to think back to Algebra 2. I need you to reflect this graph over the x-axis.
So just negative f of x.
By you reflecting, you have now put the lower number where it belongs, but he has made it into a reflection, which means that now he made it negative.
Isn't that reflecting across the y?
Y-axis, yeah. If it was x-axis, it would have just bring it down.
Think about it.
Oh yeah, because this is a y.
Yes? Okay. Next one. For the next one, for you to understand, I'm going to have to give you a graph. Okay? And it's going to seem pointless of why I would want to use it on this graph, but it's just for explanation purposes. Okay? Let's say that you have a function that's f. And let's say that this is A and this is B. Okay? How would you find, or how can I write an integral to find that area there? Integral of, hold on, just from here to here, as it is. A to B of f of x dx. You guys okay with that? Alright. That's true, agreed? That's how I would find the area underneath that curve. What if I add a random number there? So C. It's in between, right? Technically, could I find the area between A to C and add the area between C and B?
Recursion.
But I'm just having like another number. Is it true that the area from here to here, so like this right here, plus this right here, is that the same thing as all of it? Yeah, that's all it's saying. Now, the question is, why would I want to do that? Why would I want to split it up into two things? Like, what's the purpose of this property? What if you have a piecewise function where every little piece is a different function? You might want to split it into a whole bunch of them and then add it. Okay? So it becomes very helpful. And that's all I got for you today. That's it. You're not going to learn how to integrate today. So,
Integral to our success in this class.
for our quiz, which for you guys will happen on Wednesday of next week, you will need to know how to find left point sums, right point sums, trapezoidal sums. Okay, so these are all approximations, agreed? You're going to need to know how to, let me kind of flip back, use this right here. And you need to know how to find an infinite integral through the use of geometry. I mean, a definite, not infinite, I'm sorry. A definite integral through the use of geometry. So in other words, graphing it to make sure that you get a geometric shape and you know how to find that area. Okay? So that quiz is on Wednesday for you guys. That's all I got for you. Thank you for watching.